Hello and welcome to today's AWS Web Services webcast, Best Practices, Building Serverless Backends with AWS Lambda and Amazon API Gateway. Before we begin, I would like to walk the audience through a couple items. On your screen, you'll see a question pod. Please submit your questions for our presenters at any time during the webcast, and our Q&A moderator will do his best to answer them during the presentation. And we also cover selected questions at the end of the presentation. Today's webcast is being recorded. We will send you a follow-up email with the URL to the recording once we verify the recording quality, as well as a link to the presentation deck. Presenting today is Vyom Nagrani, Senior Product Manager for AWS Lambda, a compute service that runs your code in response to events that automatically manages the compute resources for you. Lambda helps developers think about applications in a new way by creating simple event handlers that respond to updates from Amazon S3, DynamoDB, Kinesis, SNS, and other services, as well as directly from web and mobile apps. He holds an MBA from the University of Michigan and has previous experience across product management, product marketing, and product engineering. Also helping today with Q&A moderation is Ajay Nair, who is also a Senior Product Manager on the AWS Lambda team. Thank you for joining us today, Vyom.
Thanks, Colin. Hey, everybody, and welcome to Best Practices for Building Serverless Backends with AWS Lambda and Amazon API Gateway webinar. My name is Vyom Nagrani. I will be your presenter for today. So let's start off by a brief overview of what both of these services are. Amazon API Gateway is a fully managed service that makes it easy for developers to create, publish, maintain, monitor, and secure APIs at any scale. With a few clicks in the AWS Management Console, you can create an API that acts as a front door for your applications to access data, business logic, or functionality from your backend services. And these backend services could be workloads running on Amazon EC2, the Elastic Compute Cloud, some code running on AWS Lambda, or any web application. API Gateway handles all the tasks involved in accepting and processing up to hundreds of thousands of concurrent API calls, including things like traffic management, authorization, access control, monitoring, version management, etc. The service takes care of all of the undifferentiated heavy lifting involved in securely and reliably running an API at scale. And it makes it easy for you to use these APIs by generating a client SDK for a number of languages, such as JavaScript, iOS, and Android. After your API is deployed, API Gateway also provides you with a dashboard to visually monitor calls to your services using Amazon CloudWatch, so that you can see performance metrics and information on API calls, such as latency and error rates, when you have an app in production. API Gateway also helps you to manage the ecosystem of third-party developers accessing your APIs. So you can create API keys on the API Gateway, set fine-grained access permissions on each API key, and distribute them to third-party developers so that they can access your APIs. The use of API keys is completely optional, and it's just an enhanced feature which must be enabled on a per method level. Lastly, APIs built on the API Gateway can accept payloads sent over HTTP. This includes typical data formats such as JSON, XML, query string, request headers, etc. Now you can declare any content type for your API response, and then you could choose a transform template to change the backend response into your desired format so that you have an easy way of translating between your front end and your backend so that neither of your systems need to change to respond to these. Let's talk about the benefits, or what's in it for you. First is that API Gateway lets you run multiple versions of the same API simultaneously so that applications can continue to call previous API versions even after the latest versions are published. API Gateway helps you to manage multiple release stages for each API version, such as alpha, beta, prod, depending on what stages you need. And specific stages and versions of an API can be associated with a custom domain name that is managed through the API Gateway. So this allows you to create vanity URLs for different deployment stages that you have, so that you can hit different stages using simple HTTP domains. Stage and version management allows you to easily test these new API versions that enhance or add functionality to earlier API releases, and thus ensuring a backward compatibility to your users in your users' transition to adopt these latest releases. This means that you can have a production API with a vanity URL sent out to all of your client users, and then no matter how many versions you publish, the API remains the same for your clients. API Gateway also helps you to manage traffic to your backend systems by allowing you to set throttle rules based on the number of requests per second. And this can be done for each HTTP method in your API. In addition, you can set up a cache with customizable keys and a customizable time to live so that the APIs that come into your system avoid hitting your backend for each request, especially if there are duplicate APIs. The third one is that API Gateway provides you with tools to authorize access to your APIs and control service operations. You can use AWS admin and security tools such as AWS IAM or Amazon Cognito to authorize your APIs. However, API Gateway can also verify signed APIs signed API calls on your behalf using the same technology that AWS uses for its APIs, which means that if you are using something like OAuth tokens for authorization for your authorization mechanism, then the API Gateway can forward your OAuth or OpenID such connect headers to the backend for verification, which means you no longer have the clients that are calling the APIs no longer need to have the Amazon SDK embedded into them. They just need to know the format of the API being called. And lastly, API Gateway tightly integrates with AWS Lambda that allows you to create a completely serverless API-based system. With API Gateway, you can create the REST API that your mobile and web applications can use to call. And these calls can be routed to AWS services through your code running in Lambda. Lambda runs your code on high availability compute infrastructure and performs all the heavy lifting and administration of your compute resources, which gives you a very powerful way of doing a serverless application. But let's talk about Lambda a little bit. AWS Lambda is a compute service that runs your code in response to events and automatically manages the compute resources for you, making it very easy to build applications that respond quickly to new information. Lambda typically runs your code within milliseconds of an event, where an event may be defined as multiple ways in which you can trigger the Lambda function. The service automatically manages the compute capacity for you and spins up and spins down the necessary infrastructure. It deploys your code and it runs the code that you provide for each event. Note that Lambda functions are stateless with no affinity to any underlying infrastructure, which means each event is processed individually, and Lambda can rapidly launch thousands of copies of the function that you provide in parallel as needed to scale to the rate of incoming events. This gives you a very seamless scalability story and maintains high performance consistently regardless of the frequency of events while still doing all of this cost effectively. For example, you can trigger an AWS Lambda function automatically to create a thumbnail when an image is uploaded to Amazon S3, since S3 put notifications can become a trigger to invoke a Lambda function. Similarly, notifications sent from Amazon SNS, or you want to verify address updates in an Amazon DynamoDB table, or you want to process clickstream data in a Kinesis stream. All of these can trigger Lambda functions automatically to run the specific algorithm or the specific code you want to run in response to those events. Lambda functions can also be invoked directly from external sources, both synchronously and asynchronously, which makes it easy to build backends to perform workloads such as image analysis, document transformation, indexing. Now, most importantly, with API Gateway, Lambda functions can be triggered by an API call made to the gateway, allowing you to build serverless backends for your applications while still managing the front end through API Gateway. So Lambda allows you to focus on building powerful, dynamic, modular applications in the cloud while not distracting your productivity in the undifferentiated heavy lifting of managing infrastructure. And that's the value that Amazon adds to the here. Lambda automatically runs your code on high availability compute infrastructure and performs all the admin of the underlying compute resources, such as server and operating system maintenance, capacity provisioning, automatic scaling, code and security deployment, patch deployment, monitoring, logging, all of these functions which are something which you could do in a DIY situation, but it makes it very easy because Lambda has done all of these once for a scale of customers so that you don't have to worry about any of these anymore. All you need to do is write code. And that's where the third value proposition comes in is Lambda now supports multiple languages. We added support for Java as a programming language in addition to Node.js with more languages to come. Our goal is to make Lambda a polyglot platform, which means a platform that supports many languages so that there is no new language for you to learn if you want to start using Lambda. Another thing to highlight is that Lambda runs your code only when needed with no unnecessary cost. This means you have an effective 100% utilization on day one and you maintain your 100% utilization when you are 3 years into your app and you are running an app in a very large scale production environment. With Lambda, you don't need to build out and maintain a fleet of servers and then pay for the time that the servers sit around and wait for jobs to run. You don't need queues. You don't need listeners or pollers that wait for new information to come to respond. All of this is managed by a single Lambda function which charges a low fee per request and runs only for the time that the code needs to run with increments of 100 milliseconds, which means if you're running a Lambda function for 3.6 seconds, you pay only for 3.6 seconds, making it cost effective to build solutions that scale from just one request per month to hundreds of thousands of requests per second. Now the combination of these two services working together is very powerful. API Gateway can act as a front end for your service with a configurable RESTful HTTP endpoint that you can share publicly or privately as you prefer, depending on what visibility you want your API to have. Lambda can act as a compute backend for the service, managing the compute resources for you and executing your custom logic only when needed, which allows you to respond to these API calls. So, without managing or setting up any infrastructure, you can build your entire application stack in minutes, and the stack will operate cost effectively at any scale. So let's talk about a few details of how the API Gateway works. The first thing we want to look at is the standard flow of the API call, including all the components of the system. So when a request comes in from a client, the client could be a mobile device, could be a web application, it could be a backend service. The request arrives at one of our CloudFront POP locations. Now this is accepted and routed through the API Gateway into the customer's region. The API Gateway receives this request and then checks for records in the dedicated cache if it is configured. And if there are no cache records available, then it will forward the request to the backend for processing. The backend, as we talked, could be a Lambda function, a web service running on Amazon EC2, or any other publicly accessible web service. In fact, you can use the API Gateway to pass through to your request to your own custom backend, which may be running on any other endpoint of your choice. Once the backend has processed the API request, all calls are logged for metrics recording in Amazon CloudWatch, and the content or the response from the backend is returned to the client. So today we are going to walk through a CRUD backend or a simple backend to support create, read, update, and delete type operations using API Gateway and Lambda. So let's start with the API Gateway. Whenever any API call is received from any client application, you can configure the API to trigger a Lambda function. Now, Lambda can respond to that trigger, and you can run your custom code to process the request. Since Lambda functions are stateless, we need a persistent data store to hold the state information. So whenever somebody creates something, we need something that actually goes and stores the information that the user created. The simple example here uses Amazon DynamoDB, a fully managed NoSQL offering by Amazon, for persisting the state behind these CRUD operations. So this is the walkthrough that we have today. Let's see how easy it is to configure this infrastructure or configure this setup on the AWS console. Note that this is the only demo we have for today, so I do recommend the audience to follow along with me on the AWS console to create a similar setup in your account as a takeaway from this webinar. All resources created in this demo would be covered by the free tier of both of these services. So there's no additional cost for you for clicking along with me. So once you sign into the AWS console and select AWS Lambda in the region of your choice, the first step is creating the Lambda function. Selecting Get Started Now or create a Lambda function will get you to this screen. We have a new approach to creating new Lambda functions in the Lambda console, what we like to call blueprints. A blueprint is a set of configuration and sample code to quickly get you started for integrating with a specific trigger. Here I select the blueprint, microservice HTTP endpoint. Now selecting this blueprint pre-configures some of the mapping and the sample code for you. In this second step, let us give a name and description to the Lambda function that we want to create. Note that my examples are currently written in node.js, but the runtime dropdown over here will allow you to pick Java as a programming language. So we welcome Java programmers to have at it and follow through using a Java example, though the blueprint is currently configured only for, the sample code is available only for Node.js. Also note that for creating a function, Lambda gives you three options. The first one is to edit the code inline, which gives you a WYSIWYG type editor where you can directly start typing the code. The blueprint that we have selected has some pre-configured code in here, so for this blueprint you don't need to actually write the code. But you can also upload your code with any additional dependencies or binaries in a zip file directly to the Lambda console. This allows you to package lots of NPM modules into your code if you want more complex stuff written in here to respond to your APIs. Alternatively, you can also upload the zip file to S3 and provide the S3 object details as a source of your Lambda function, which allows you to integrate your custom deployment tools directly with AWS Lambda functions. As I mentioned, the Lambda console provides code templates for different event types or triggers, including Amazon services that Lambda integrates with, as well as for direct invokes. The blueprint that we selected pre-populated the sample code for creating the compute setup for the CRUD backend. Let's zoom into the code a little bit to see what the code looks like. Instead of doing a full walkthrough of this code, let me just show you the highlights. As you can see here, all the code does is remove the operation from the operation object from the event object, so that the same event object can then be used to pass along the remaining data to the data store for further operations. The data store that we have selected here is an Amazon DynamoDB, which you can see as creating a new DynamoDB doc at the start. We then go through a switch case to identify the operation that we need to run and pass the CRUD operations and the remaining event object to DynamoDB with the proper DynamoDB API being called. As you can see here, for example, a create goes and does a dynamo.put item, whereas a read will go and do a dynamo.get item. The benefit of doing something like this is if you choose a different object store instead of DynamoDB, all you have to do is replace the Lambda code for the API calls being made to the data store. The actual API interface that your clients see will not change. We've also added a few extra options in here like echo and ping pong to test the function when ready. And lastly, there is a catch-all for error handling in case the user provides any incorrect inputs. So, and the next step of the AWS console, a few additional configuration changes you would need to make in step 2 are listed here. The first configuration on the Lambda console is to select the execution role for the Lambda function. This is a permission to allow Lambda to take action on your behalf by interacting with other AWS services. For example, Lambda function needs to read and write data to DynamoDB and put data to CloudWatch logs for any logging. So the Lambda console provides an easy template for creating these execution roles, or if you already have one, you can select an existing role. There's another step in here for selecting the memory you want to allocate to your function and the timeout you want to set. Let's leave these two values to default right now, and we'll come back to fine-tuning these. Let's look at the role creation one a bit more. Say we selected create a new execution role. The Lambda console automatically redirects you to the IAM console of AWS with a pre-populated policy document. You can change the role name here in the IAM console. You can expand or edit the policy to add more options. But here's a quick look at the policy document. As you can see, the policy document does two things. One, it allows Lambda to make changes to CloudWatch logs, and this is for logging your Lambda function calls inside of the Lambda console. And the other one is to allow Lambda to read and write to DynamoDB, and this is for storing the actual CRUD operations. Now, when you click allow on this IAM console page, it will automatically take you back to the Lambda console with this policy created and attached to the Lambda function that you are creating. Step 3 is where you define the actual configuration of the RESTful HTTP endpoints for this Lambda function. Behind the scenes, what's actually happening here is this is creating and configuring the API gateway and deploying the API on your behalf with these configuration details. Again, except for entering an API name, we'll leave the other settings as default, and we'll come back to what these are. You note that you should always have your security as open with access key. If you haven't set throttle controls for your API, because otherwise anybody who has access to your API name or your API endpoint can start flooding you with requests, and all of the requests would go to your backend. When you click next, the last step that you'd see is just a verification of all of the configurations that you have set. If everything looks okay, you can select create function, and most of the configuration will be done for you. The only additional setting I have in here is, which I have done already, is I have a table created in DynamoDB called myTable with the primary hash key set as ID, which is a string value. So once the function is created, it'll take you to a screen which shows you what you want to do next with your function. This is a screen where you can start testing your function within the Lambda console before moving over to the other console, so that you can run a local test within the Lambda console. So if you select actions within this test screen, you can select an option of testing, which allows you to throw different event types to the Lambda function. Now, whenever the Lambda function is invoked, it gets two event objects. It gets the event object and the context object passed along to it. So this screen allows you to configure that event object that the Lambda function would get. In regular operations, this event object would come from the actual HTTP headers of the API gateway calls. But this allows you to configure these options for local testing. As you can see here, I select the operation in here to set as echo. From the Lambda function code, we remember that they should just delete that operation and then echo back the remaining two event objects back to us. So when we hit submit, you will see that the Lambda console will show a successful result with the two remaining objects sent back to you as the response to the object. It also generates a summary of how much time your function actually took for executing and the actual memory used. It also gives a log output of what your function did, and this is where we need the CloudWatch logs for. So now let's move to the API gateway screen. So on the API gateway screen, you will notice that even though you haven't created anything, because the Lambda console has created these for you, you will see a API which has already been created and ready for you to use. In this console, what we want to do is we want to test our Lambda function from here to see how that Lambda, to test our entire stack from here using the test functionality of the API gateway. So when you select the test option, it will allow you to add a request body that goes into your API call. So I do the exact same thing from here, is that I call the echo operation from here. The only difference is that now this echo operation is going to get passed from the API gateway to the Lambda console, which means we are doing an integration test over here. Now when I click the test button, I will see the response that comes through in the API gateway console. And this response is actually coming from the Lambda function behind the scenes. And it's the exact same response which we got earlier. But let's test a few other parameters. For example, this time, instead of doing a simple test, I'm going to simple echo, I'm going to do the operation as create. Now because I'm doing an operation as create, in the backend, my switch case in my Lambda function is going to push the remaining event to DynamoDB. Therefore, the remaining objects inside the test event, the test object, need to look like a DynamoDB put record. So what I'll have is a table name as my table, the item with a primary key of ID as test01, and the actual value that I'm going to add in is a comment as test number 01. Now when I click test on here, the response body is going to be null because there is nothing that the Lambda function is returning over here. But what you can do is if you go and look from here into the DynamoDB console, you will see that in your table called my table, there was a new item created called test01 with a comment saying test number 01. So what we can do next to test the functionality from the API gateway is we can go and read that object. So we do the exact same test again, except that this time we change the event object to say operation as read. The table name stays the same, and the key is simply saying get me the ID for test01. Note that we are not saying what the content should be here. We are asking it to read what the content behind the ID test01 looks like. Here, when we hit test, you can see that the response object is actually fetching the data from DynamoDB and returning it to the API gateway. So here you see that the comment is available in the response body at the bottom of the screen. So what you saw is that something that was created in Lambda can create things on both sides of the stack. The API gateway, when you're passing a request body, calls the Lambda function. The Lambda function executes that code. It goes and calls DynamoDB to store the actual data or to retrieve the actual data. The data comes back to Lambda, and then Lambda passes that data back to API gateway. And this entire stack was created in just a few clicks. A few additional settings that you could set in the API gateway that I'd like to walk through is if you go to stages at the top of your screen in the API gateway and select the prod stage which was just deployed, you get a few additional settings. The first is to enable a API cache. The caching allows you to cache all of the data that's coming in from your backend, so that any requests which come in which are exactly the same to the API don't have to hit the backend again. The other functions also allow you to enable more detailed logs and metrics for your API gateway functions, which allow you to track specific APIs or specific stages if you want. The last one is throttle settings. This allows you to set a burst limit and a rate limit to your APIs. This is to protect any brownouts to your backend services if you're running your own custom endpoints. But if you do this with Lambda, then these aren't needed because Lambda scales automatically with the rate of incoming requests. Another key point to look in here is that the second tab called SDK generation. The API console for a specific stage will also allow you to generate a client SDK for all of the APIs that you have under that stage. Right now, we only have one API which we have created called the example function with HTTP endpoint, which has a post method associated with it. So that SDK here is going to be pretty simple, but as you add more SDKs to the same stage, you can generate an entire client SDK using this functionality, and therefore you don't need to have the actual AWS SDK which embedded inside your client. It can be a much lighter SDK which only exposes the APIs that you want to expose. Now all of this is still using the API Gateway console as a front end. To showcase what's possible with this new integration and just how easy it is to build an actual service with a public endpoint that runs entirely without servers, we built something called Squirrel Bin. Squirrel Bin is a simple website that allows users to run CRUD-like little nuggets of code that we like to call acorns. Here's the architecture that goes behind Squirrel Bin. If you see, it's very similar to what we just put together. All of the clients can call the API gateway, and the API gateway behind the scene runs these acorns or the get operations or that have different put, delete type of requests that end up going to a Lambda function. The Lambda function behind the scenes talks to DynamoDB to actually get these data. The additional difference that we have done in here is that we have created a vanity URL using Route 53, which allows you to front this with a simple user-friendly URL like squirrelbin.com, which you can share with your external customers. But behind the scenes, this is really just calling the APIs. Notice what isn't in the diagram above: servers. In fact, no infrastructure is required for any part of this experience. There is a clean separation between the data management and the presentation. Now, the website itself is fully client-side, single-page app written in Angular and hosted statically on Amazon S3 with a DNS managed by Route 53. To manage the acorns, the app makes a REST API call to the API gateway. These endpoints then trigger the Lambda functions that interact with Squirrel Bin's underlying DynamoDB acorn store to run the actual acorn code. Note that because Squirrel Bin's APIs are completely separate Lambda-powered stack, it will be easier to create additional clients. So instead of having the same client having a switch case, the same Lambda function doing a switch case through the different APIs, we have different APIs going to different Lambda functions. This allows you to quickly scale and add more APIs on this Lambda-powered stack and create additional clients, such as an iOS app that calls the Lambda functions, or via the mobile SDK, or an Alexa skills kit that allows you to run the acorns using your voice commands. This function is built using a blueprint that we just created, with the only difference being that the code running in this Lambda function behind the Squirrel Bin runs a JavaScript eval instead of the actual function. Since this is a public function that anybody can run, and for security purposes, it's an eval rather than directly communicating with the DynamoDB. However, we do encourage you to go to this site. It's a simple squirrelbin.com and see the API gateway and Lambda work together. So we've looked at the how to start part of integrating Lambda functions with the API gateway. Let's look at the behind the scene details for the advanced configurations for attaching Lambda functions to the API gateway. The first thing I want to call out is a one-to-one mapping, which means every API that you call triggers a stateless Lambda function, and that Lambda function would be a copy of the code that you have provided for the integration. This allows you to very easily and quickly scale out your application. If you have one request coming in per day versus if you have 100,000 requests coming in per second, the setup that you have looks exactly the same. An additional parameter to call out is that you can add caching to your API calls that would return a cached response instead of having duplicate requests come in. This can be used if you have complex functions which you are running in the backend, and you just don't want to load your backend for duplicate requests, especially when the cache can handle can handle those requests. This allows you to have your front end be much more responsive than your backend, and therefore allowing you to do things much faster with lower latencies and lower cost. Two quick callouts on API gateway concepts. Now, an API is defined as a set of resources and methods. And these map to the standard definition of any API. A resource is a logical entity that can be accessed within an API, whereas a method is the combination of the resource path and the HTTP verb such as a get or a post. So the resources in your API could, for example, be cars, and then you could have methods saying get cars or post cars, which will just change the API behavior accordingly. Last one to call out is automatic scaling. Both API Gateway and Lambda scale automatically with the number of calls coming in. And this is the value that these two services bring out by integrating very closely together. Which means that the same setup that you have for running this one or two test APIs that we just walked through to the console, without making any changes to the setup, you can have the same setup run for 100,000 transactions per second, where all of these requests are coming in, hitting your production stack. I do call out that there is a safety throttle of 100 concurrent Lambda functions. The only reason we have this throttle in place is to protect users from runaway functions or runaway code during your dev or test cycles. So this might introduce a little bit of friction to scale up at the start, but what you would notice that as you get bigger, this throttle limit starts going away, and you can always have this limit increased by contacting the AWS Support Center if you don't want this limit in the first place. The API Gateway also has a user-defined standard limit and a burst rate limit per second for each API method if you want to add an additional level of protection to control your costs if you have an open function which you don't know who's going to be calling. Let's talk about a few best practices for creating the Lambda functions themselves. The first is the memory. Lambda allows you to select memory in starting from 128 megabytes all the way up to 1.5 gigabytes per Lambda function in increments of 64 MB. The memory is simply a control of the processing power or the capabilities of the function that you have, since Lambda allocates CPU proportional to the memory that is configured. Which means that increasing memory makes your code execute faster if your application or your response to the API is CPU bound. Second one is timeout. Increasing this timeout allows you to run longer Lambda functions. The current default timeout is 3 seconds for other Lambda functions and 10 seconds for an API Gateway function, but you can set this all the way up to 60 seconds if you want to have functions which run for up to a minute to respond to an API call. This allows you to call for APIs which don't really have a very high latency limit, but would rather have an answer even at the end of 60 seconds. Lambda also has a concept of retries for most other functions, but for the API Gateway, Lambda doesn't retry the function execution. And this is because the API Gateway calls the Lambda functions synchronously. And we don't want to retry a function where somebody is making a synchronous call and the synchronous call already has been terminated. However, the gateway generated SDKs, which is the client SDKs which you generate from the API Gateway console, will retry throttled executions, which means if you have a throttle limit set either on your API Gateway or on your Lambda function, if the client that's calling your function, calling the Lambda function gets a throttle error, it will retry the code that without the client having to do any changes to the client application. Lastly, in terms of permission model, the API Gateway synchronously triggers Lambda. So what we need here is to assign the API Gateway a resource policy to invoke the Lambda function. This is done automatically if you are configuring the Lambda function either using the API Gateway console or the Lambda console. This setting is important only if you are setting this up using the CLI or directly using the AWS APIs of the API Gateway and Lambda. The Lambda console also has a console dashboard, which lists all your available Lambda functions and provides an easy way of editing your resources, event sources, and all other settings associated with your Lambda function. The Lambda console also has an at-a-glance metrics dashboard, which shows the last 24 hours of things like your latency, your request count, your error count, and your throttle count. Note that all of these metrics are also available through a CloudWatch logs console. If you click the CloudWatch console, if you wish, the CloudWatch console will store these data for whatever time you want these data to persist. So you can go from Lambda to CloudWatch to look at all of these errors, the history of all of these metrics. Also note that all of Lambda logs are automatically forwarded to CloudWatch logs. So these are the settings on the Lambda console. Let's look at a few of the other options that you have on the API gateway. The first one is how request and response data can be transformed in flight. Now we use Apache Velocity as a standard to create, save, and execute templates. Now, we have been working with our customers on this during development, and we have seen a few use cases of how input-output can be transformed for achieving different behavior. The first one is to filter API responses. And in many cases, legacy APIs tend to return verbose responses with too many objects embedded into that. Now, large payloads are a struggle for mobile applications. So users can use this template to traverse the response schema and filter out the output to return only the necessary fields, which will drastically improve the API performance from the client application, such as a mobile client or a web browser. The other one is to convert RPC type request responses to REST type request responses. The users have been using RPC style APIs when they wanted to expose to the world, and they want to change that to form a RESTful API. The RPC often accepts only post calls. So users use the transform templates to accept a get call in the API gateway and then generate a post body for their backend call to read the parameters for the path, query string, headers, etc. in your call. Last one is for customers who want to leverage Lambda but run only XML. Lambda is completely built using JSON as an input because it uses the object events and the context events as JSON objects. APIs have been using the transform templates to receive the JSON output from Lambda and then turn it into XML before sending it back to the end user. This can allow users to completely switch to your backend technology with no disruption to the front-end APIs being called, so that the third-party developers utilizing your APIs will never see the difference, even though the backend system has been changed from XML to JSON. The next one is versioning. Here's a visual representation of how versions and stages are managed by the API gateway and how users can leverage these features for building APIs. The first thing you do is so let's take a sample use case of where first thing you do is declare a V1 API and start configuring its resources and methods. Next step is to deploy the API to a development stage. So we'll keep deploying to development as we evolve our API. At a certain point, when you feel that you are ready for third-party integrations and third-party developers to access this API, you'd push this to a production stage and then distribute the API keys and the generated SDKs along with it. All along, we are still continuing to deploy the API to both your dev and prod stacks, including new features and bug fixes. At some point, you would want to make some breaking change and work on a much improved V2 API. However, we cannot make the breaking change to API in production because you might have thousands of developers or clients who are already using that API. To manage this situation, what you could do is you could simply clone the current state of the V1 API and call it the V2, and then begin development of this new version. By cloning, you can keep publishing bug fixes to the first release and support users who are still calling your V1 API and in the prod stage, but you no longer have to touch your V1 dev stack. Then over time, you can, with a gentle gradual deprecation, stop pushing the releases to your V1 as your clients start upgrading to your V2 prod endpoint. And remember, in the meantime, you still have a V2 dev stack in which you are doing your latest development. Now, customers can configure the API gateway to use a custom domain name instead of the standard AWS domain. We expect users to bring their own signed certificates for HTTPS endpoints, but domain names can be configured to point to an API, to the top level item, or directly to a stage within API. So you could choose either of those. So pointing a custom domain name to an API requires that the stage be included in the path, which means if the domain name is pointed directly at a stage, there is no need for the path variable, but resources can be directly accessed from the root slash. But if you have a specific stage you are talking to, then you could go to /prod and point your custom domain name to that stage. Lastly, I'd also like to call out that a similar native versioning functionality is going to be available soon on AWS Lambda, which will allow you to create aliases and versions for functions inside of Lambda, so that you can directly hook up your API stack prod endpoint to a Lambda prod endpoint, allow you to manage your versions very easily behind the Lambda functions. So in summary, we have 3 next steps for you. First, we do encourage you to create and test your first API if you already weren't following along on our console. With a few clicks in the AWS Management Console, you can create an API that acts as a front door for your applications to access data, business logic, or functionality from backend services. Second is that we invite you to create and test your first Lambda function. With AWS Lambda, there are no new languages, no new tools, no frameworks to learn. You can even bring third-party libraries, or you can inbuild native libraries for Node and Java, so that you can start programming in your language of your choice. And if you do use both of these services, we encourage you to select Lambda as a backend for your API, because this gives you a simple endpoint for your function, which can respond to REST calls like get, put, post, without ever managing any servers or any infrastructure. So I really do thank all of the users for attending this webinar. I hope that you were able to get something out of the webinar. We have the Q&A questions, which we are still going, but I'd invite all the users to visit any of these links over here if you have any follow-up questions outside of this webinar. I also want to highlight that if you're interested in learning more about how to navigate the cloud and grow your business, please register now to view the live stream broadcast of the October 7th AWS reInvent keynote and the October 8th AWS reInvent keynote, and select technical sessions both on October 7th and the October 8th. Register today by entering your email ID in the link which we have on this page. You will receive additional information from us and reminder emails as we get closer to the event. Alternatively, to register, simply go to https://reinvent.awsevents.com/index.html with a tracker URL. You could scroll down to the AWS reInvent homepage and enter your email ID where prompted. The reInvent live stream broadcast registration is free. So there are no additional charges for you to register and view the reInvent keynote sitting in the comforts of your offices.